Hi, welcome to History Connected. You know, sometimes history doesn't move in a straight line. It takes incredible turns and twists. For instance, look around you. Everything feels solid, predictable. The desk beneath your hands, the sunlight streaming through the window. It's all so steady, so certain. The universe behaves just as you expect it to. But what if it didn't? Beneath the surface lies a stranger reality, a world where particles flicker in and out of existence, where small changes create chaos, and where simply observing can alter what's real. The search for order, for answers, isn't new. It's been humanity's quest for thousands of years, driven by curiosity and necessity. Sometimes it begins with the grandest of questions: what holds the stars in place? What shapes the heavens? And sometimes it begins with something far more practical, like a problem faced by the people of Athens, a growing city desperate for a solution. The answer they found didn't just solve their problem, it gave birth to something extraordinary. And the problem? Water. Athens had a problem, a big one: water. Sure, the city was growing, the economy was booming, and its influence spreading across the ancient world. But when it came to basic survival, Athens was running dry. Unlike other cities blessed with rivers or natural springs, Athens had to scrape by with a fragile network of wells and cisterns. And as the city's population grew, so did the demand for water. So what did they do? They got creative. To bring water from distant springs into the city, they needed precision. They had to measure distances, calculate slopes, and align channels with remarkable accuracy, all without modern tools. Too steep, and the water would rush out of control. Too shallow, and it wouldn't flow at all. This wasn't just digging a ditch. The Athenians turned to geometry, practical geometry. Using simple tools like ropes, rods, and weighted strings, they calculated angles and gradients, ensuring water could flow smoothly into the city. It was a perfect example of necessity driving innovation. Around the same time, over on the island of Samos, a Greek engineer named Upalinos faced an even greater challenge. His city needed water, and the only way to get it was to dig a tunnel, nearly a kilometer long through a mountain, starting from both ends, with basic tools. Somehow, Upalinos got it right. His two teams met perfectly in the middle, creating a marvel of ancient engineering. Back in Athens, water wasn't just for drinking. It fed the city's sacred rituals, its fountains, and its civic life. Solving the water problem wasn't just about survival, it was about order, structure, and control. And the key to it all was geometry. Geometry started as a tool for survival, a way to build wells, aqueducts, and temples. But in Athens, it didn't stay practical for long. The Athenians were a curious people, and when they saw how these tools could solve problems, they began asking bigger questions. What else could geometry do? Could it explain more than just water? Take Thales of Miletus, for example. He wasn't an Athenian, but his ideas flowed into the city like the water they were so desperate for. Thales showed that you could calculate the height of a pyramid just by measuring its shadow. To the Greeks, this was magic. Geometry wasn't just useful, it was powerful. And in Athens, power meant ideas. Soon, philosophers weren't just solving problems, they were debating the meaning of circles, triangles, and ratios. Pythagoras, one of the most influential thinkers of the time, declared that numbers weren't just tools, they were the essence of reality. He believed that the universe was governed by a mathematical harmony, like a cosmic symphony, where everything moved in perfect ratios. The Greeks began applying geometry to the heavens. Eudoxus of Cnidus, a student of Plato, imagined the planets moving in transparent spheres, each spinning around the Earth in perfect harmony. To him, geometry wasn't just about building aqueducts, it was about unlocking the secrets of the cosmos. And it wasn't just the philosophers. Athenians used geometry to align their temples to the heavens. To them, math wasn't just practical, it was sacred. Every shape, every angle, every measurement connected the human world with the divine. What began as a way to channel water had transformed in a way to channel ideas. Ideas that would inspire not just engineers and architects, but also philosophers and astronomers for generations. Geometry wasn't just a tool anymore. It was a window into the nature of the universe itself. Take the followers of Pythagoras, for instance. They weren't just measuring things. They believed numbers held the key to reality. To them, a triangle wasn't just a shape, it was a clue. Pythagoras even claimed that music, the stars, and the human soul all followed mathematical ratios. He called it the harmony of the spheres, the idea that the universe itself sang, its planets moving in a cosmic harmony. Then came thinkers like Eudoxus of Cnidus, who took Pythagoras' dream and gave it form. He imagined the planets fixed on transparent spheres spinning in perfect geometric patterns. Each planet's motion followed mathematical laws, like the ticking of a celestial clock. It wasn't perfect, but it was a start, a way to use geometry to map the heavens. For Plato, this was no surprise. He believed the physical world was just a shadow of a higher, perfect reality, a reality defined by geometry. To him, understanding math was like glimpsing the divine. It was a way to see the unchanging forms behind the messy, imperfect world we live in. And the astronomers agreed. They traced the stars' movements using geometry to predict eclipses, chart constellations, and measure time itself. What they found only reinforced the idea that the universe was orderly, harmonious, and above all, knowable. In Athens, geometry wasn't just math anymore. It was philosophy, a religion, a science. The Greeks believed they were uncovering the very code of the cosmos, an idea that would echo across centuries, shaping the way we see the universe today. For centuries, the brilliance of Greek geometry sat in silence, locked away in monasteries and libraries. The ideas that had once mapped the heavens and explained the cosmos were all but forgotten, until someone blew the dust off. Enter Nicholas Copernicus, a scholar who found himself mesmerized by the geometric theories of the Greeks. He pored over texts by Pythagoras and Eudoxus, studying their models of the cosmos, but something didn't sit right. Their Earth-centered universe was elegant, yes, but it didn't match what he saw in the sky. So Copernicus did something radical. He flipped it. He placed the sun at the center of the cosmos, and suddenly everything clicked. Copernicus's heliocentric model wasn't perfect. It still relied on circles when ellipses would have been closer to the truth, but it set off a chain reaction, one that would lead to the Renaissance and beyond. Decades later, Johannes Kepler would refine Copernicus's ideas. By studying precise astronomical observations, Kepler realized that planets didn't move in circles, they followed elliptical orbits, governed by mathematical laws. This discovery was shocking. How could the cosmos be both orderly and imperfect? Kepler saw it differently. To him, the elliptical orbits were proof of a deeper harmony. Then came Isaac Newton, who we've talked about quite a bit on this channel. He brought it all together. Using geometry and calculus, he showed that the same force pulling an apple to the ground also kept planets in orbit. Newton's laws of motion revealed a universe bound by gravity, where everything, on Earth or in the heavens, followed the same mathematical rules. What started with the Greeks had come full circle. Their geometry had inspired Copernicus to reimagine the universe, Kepler to refine it, and Newton to prove it. The dream of a perfect cosmos, driven by mathematical principles, had become a reality. Or so it seemed. Imagine this, a game of dice, players leaning in, hoping for a lucky roll. For centuries, gambling was all about chance, unpredictable, unknowable. But in the 1600s, two mathematicians dared to ask, what if luck isn't random at all? Enter Blaise Pascal and Pierre de Fermat, who turned their attention to games of chance. By analyzing dice rolls and card draws, they uncovered patterns hidden in the chaos. Their work gave birth to probability theory, the idea that where individual events might seem unpredictable, patterns emerge over time. For gamblers, it meant calculating odds. For mathematicians, it meant something bigger. Randomness could follow rules. A few decades later, Jacob Bernoulli pushed probability theory further. He discovered the law of large numbers, showing that while single events are chaotic, large samples smooth out into predictable patterns. Toss a coin a few times, you might get streaks. Toss it a few thousand times, and it's almost always 50-50. Bernoulli had uncovered a hidden structure in randomness. And it wasn't too long before these ideas escaped the gambling halls. Statisticians in London used probability to analyze life expectancy, tracking births, deaths, and diseases. Suddenly, human lives, once thought to be governed by fate, were being measured, averaged, and predicted. By the 19th century, Adolphe Quetelet was applying probability to society itself. He coined the idea of the average man, using statistics to describe traits like height, intelligence, and even behavior. What Quetelet saw wasn't randomness, but patterns, regularities that defined entire populations. And it didn't stop there. In the industrial age, economists used statistics to optimize production, measure efficiency, and even predict market trends. Probability had transformed from a gambler's trick into a tool for understanding everything from economics to epidemics. What started as a curiosity about dice had grown into a way to see patterns in the world, patterns that link chaos to order. But just as we were starting to see the rules in randomness, science revealed an even deeper mystery. At the smallest scales of reality, probabilities weren't just useful, they were fundamental. By the 1900s, physicists thought they had figured things out. Newton's laws explained the motions of planets and apples, and probability theory had tamed randomness. But as they looked deeper into the atom, the familiar rules of physics started to crumble. It started with Max Planck, who discovered something unsettling. Energy wasn't continuous. Instead, it came in tiny, indivisible packets he called quanta. It was as if the universe operated on a grainy, pixelated scale, and this pixelation defied everything classic physics stood for. Then Niels Bohr studied electrons and made things even stranger. Electrons didn't orbit the nucleus in smooth paths like planets around the sun. Instead, they jumped, literally quantized, from one energy level to another without passing through the space between them. It was like climbing stairs without touching the steps. Next came Werner Heisenberg, who found that even the smallest particles couldn't be pinned down. His uncertainty principle showed that you can't measure both the particle's position and momentum at the same time. The more you know about one, the less you know about the other. It wasn't just a technical limitation, it was a fundamental property of the universe. These discoveries led to a radical new idea. Particles like electrons don't exist in fixed positions until they're observed. Instead, they exist in probability clouds, where their location and behavior are spread out as possibilities. Observing them forces them to choose a specific state, collapsing the cloud into a single point. Quantum mechanics had rewritten the rules of reality. At the smallest scales, certainty was an illusion. Particles didn't follow Newtonian laws or even classical probability. Instead, they obeyed quantum probabilities, revealing a world where outcomes were never guaranteed, or even likely. If you've ever watched light reflect off water or pass through a window, you know it behaves like a wave. That's what scientists thought for centuries too. Light, they believed, was a wave, bending and bouncing around. But then came a twist, one of the strangest in science. Sometimes light acts like a particle. The discovery came in 1905 when Albert Einstein studied how light could knock electrons free from a piece of metal. This wasn't wave behavior, it was something else entirely. To explain it, Einstein proposed that light comes in little packets of energy called photons. Think of photons as tiny bullets of light. This was a shock. How could light so clearly be a wave but also be a particle? But this was just the beginning. Scientists later performed an experiment with electrons, tiny particles of matter. They fired these particles at a barrier with two slits, expecting them to behave like tiny marbles. Instead, something astonishing happened. The electrons created an interference pattern, just like waves of light. It was as though each electron passed through both slits at once, spreading out like a wave. So were electrons waves? Not exactly. Here's where it gets even stranger. When scientists placed detectors at the slits to measure which path the electron took, the interference pattern disappeared. The electrons now behaved like particles, not waves. In other words, the mere act of observing changed their behavior. It's as if the universe was saying, if you watch, I'll show you one thing. If you don't, I'll show you another. This baffling behavior forced scientists like Erwin Schrödinger to rethink how particles behaved. Schrödinger came up with an idea. Particles don't exist in one place or another. Instead, they exist as waves of probability. Potential outcomes spread across space like ripples on a pond. And only when you observe them do they choose to define their position. Wave-particle duality wasn't just a quirky discovery. It rewrote the rules of physics. Light wasn't just a wave, it was a particle. Electrons weren't just particles, they were waves. Reality, it turned out, wasn't as solid or as predictable as we thought. And if you think that's strange, wait till you hear what comes next. Let's talk about chaos. Not the kind that involves broken dishes or bad Mondays, but the kind that governs the weather, the stock market, or even the way leaves scatter in the wind. For centuries, scientists thought that if you had just enough data, you could predict anything. But in the 1960s, a meteorologist named Edward Lorenz stumbled onto a discovery that would blow that idea apart. Lorenz was working on weather prediction. He typed a slightly rounded number into his computer, a tiny shortcut, and he hit a home run. When the simulation finished, the results were wildly different from his earlier run. Same equations, almost the same starting numbers, but a completely different forecast. What Lorenz found was startling. Small differences in initial conditions could lead to huge differences in the outcome. This sensitivity to initial conditions became known as the butterfly effect. The idea that something as tiny as a butterfly flapping its wings in Brazil could eventually trigger a tornado in Texas. This wasn't just about weather. Lorenz's discovery revealed that in complex systems, tiny changes could ripple outward, creating patterns that were impossible to predict precisely. This realization gave birth to chaos theory. Not long after, Benoit Mandelbrot added another layer to this. Mandelbrot studied chaotic systems like coastlines, clouds, and snowflakes, things that looked messy and random but seemed to follow hidden patterns. He used computers to visualize these patterns and discovered something remarkable. Within the apparent chaos, shapes repeated at every scale. He called these shapes fractals. Fractals were more than just pretty shapes. They showed that chaos had a kind of order, a structure hidden beneath the surface. And this wasn't just about math. Ecologists found fractals in animal populations, economists in stock markets, and even cardiologists in the rhythm of your heart. Chaos theory wasn't random at all. It was the science of finding patterns in the unpredictable. Lorenz's butterfly effect and Mandelbrot's fractals revealed a truth that felt counterintuitive. Even in systems that seemed chaotic, there was structure, if you knew where to look. It was kind of a hidden harmony, one that echoed the ancient Greeks' search for order in the universe. By now, you might be wondering, if chaos theory showed us hidden patterns in the unpredictable, could something similar be true at the quantum level? The answer is both fascinating and unsettling. At the smallest scales of reality, the rules of the universe aren't just chaotic, it was probabilistic, or based on probability. And yet, even in this uncertainty, there's a strange kind of order. Let's start with Niels Bohr. He discovered that electrons don't move in smooth continuous paths. Instead, they jump between energy levels in discrete steps, like hopping between the rungs on a ladder. It was a neat and tidy model until physicists started digging deeper. Enter Werner Heisenberg. He discovered something that shattered the illusion of precision, the uncertainty principle. At the quantum level, you can't both know the exact position and the momentum of a particle at the same time. The more precisely you measure one, the fuzzier the other one becomes. It wasn't a flaw in our tools, it was a fundamental property of the universe itself. This means that particles like electrons don't have fixed positions until we observe them. Instead, they exist in a probability cloud, a range of possible locations and energies. Only when we measure them do they collapse into a single state. If this sounds familiar, it should. Chaos theory taught us that even in unpredictable systems, there are patterns. Quantum mechanics revealed something similar. Particles don't move randomly. They follow probabilistic rules. Over time, patterns emerge. Electrons might appear unpredictable individually, but as a group, they form clear, statistical patterns. In other words, there's order within the uncertainty. Erwin Schrödinger's wave function captured this beautifully. His equations didn't describe where particles were, but where they might be. It was a radical idea. The universe at its small scale isn't deterministic, it's probabilistic. And yet, from these probabilities, the world we know emerges. In chaos theory, we found order hidden within the complexity. In quantum mechanics, we found probabilities that create patterns over time. Both fields forced us to rethink what order means. It wasn't the rigid clockwork of Newton's universe. It was something deeper, stranger, and more dynamic. It began with order, a simple need, to bring it where it was scarce. It sparked a revolution in thought. Geometry turned from a practical tool into a way of understanding the world. The Greeks used it to map the heavens, searching for harmony in the stars. Their ideas echoed across centuries, inspiring Renaissance astronomers like Copernicus and Kepler, who uncovered the mathematical laws of the universe. For a moment, it seemed the cosmos were a perfectly ordered machine. But then came randomness. Probability theory showed that even in chaos, patterns emerged over time. Mathematicians revealed that uncertainty wasn't a barrier to understanding, it was part of it. At the smallest scales, quantum mechanics replaced certainty with probabilities. In larger systems, chaos theory uncovered patterns hidden in disorder. Together, they revealed a deeper truth. The universe isn't simply orderly or chaotic, it's both. From Athens to atoms, humanity's search for harmony led to a paradox. Beneath chaos lies structure, and behind structure, uncertainty. The Greeks imagined a cosmos ruled by perfection. What we've found is more complex and perhaps more beautiful. The universe dances between chaos and order, chance and pattern. But if the universe is both ordered and chaotic, is harmony something we find? Or is it something we create? Hi, this is Charlie. I just want to say thanks for watching. If you like what you saw, like, subscribe, hit the notification button, and leave a comment. Also share it if you know anyone who likes history. I'd really appreciate it. And until next time, be good.